Welcome. In this video we are going to present the CFD model of a blender. In this project the objectives are to model the blender's blade in CFD and to model the liquid-gas interface for water and honey.
For the development of the project, a cut of a blender was given to the group. Some modifications were made using Autodesk Inventor in order to avoid the overlapping of the internal parts of the blender. Then the internal volume was extracted.
To begin with the simulation, it was important to define the regimen with which the flow was going to behave. For this calculation, one used the equation shown above and resulted in a Reynolds value of 168,089 for water and 35 for honey. Therefore, given the Reynolds intervals, one can say that the water flows with a turbulent regimen and honey flows with a transition regimen. Finally, in order to find the time step necessary for both water and honey, the following calculations were made. First, one converted the revolutions per second to radians per second using the equation shown in the slide. Then, the total desired time multiplied this value and it was converted to degrees. In order to find the time step value, one cross-multiplied the total time, total degrees, and degrees specified for each substance to obtain its respective time step.
For the mesh were used 321,000 polyhedral cells with a high to medium quality. For the velocity profile, it is observed that the propagation of velocity in the water is slow. One can see that the blades have a greater velocity than the surrounding fluid. The blades are encapsulated inside the lower cylinder, so in that part of the blender, the change in the speed is greater than in the total volume. Also, an increase in speed can be observed on the solid-liquid interface. As it will be seen next in the zone near to the wall, higher velocities are obtained than those of the rest of the volume. This is caused by the formation of the vortex that will be shown in detail in the following image. For the volume fraction of liquid, it is observed that the propagation of speed is low, causing a slower vortex formation. On the other hand, the presence of softened baffles do not allow the complete reduction of the vortex. An important transition zone is observed in the liquid-gas interface, where there is an important mixture between the gas and the liquid. It is not observed that the interface is mixed with the liquid and gas phases.
For honey, it can be observed that the propagation of speed is greater than in water. This is due to the high viscosity of honey. In addition, unlike water, in honey one can see a more defined profile for speed. The magnitude of the speed is greater since a shear effort is being made. Having a high viscosity, the speed is transmitted much easier. Unlike water, the formation of the vortex is more defined for honey and the maximum speed is in the middle of the vortex. Finally, the behavior of the vortex decreases the velocity after it reaches the maximum speed value. In the case of the volume fraction of liquid in honey, a defined and more pronounced vortex formation can be seen. In addition, the gas-liquid interface is not uniform as its thickness decreases as it approaches the blades. In conclusion, unlike water, it can be seen that for honey corresponding to the most viscous fluid, the vortex formation is more noticeable in the velocity profile, and it is observed that the velocity is transmitted faster.